Chapter 11, the t-test for two related samples, Part 4. Often, a close look at the sample data from a research study makes it easier to see the size of the treatment effect and to understand the outcome of the hypothesis test. In example 11.1, we obtained a sample of 9 participants who produced a mean difference equal to -2, with a standard deviation equal to 2 points. The sample mean and standard deviation describe a set of scores centered at mean D equal to -2, with most of the scores located within 2 points of the mean. This figure 11.4, shows the actual set of different scores that were obtained in example 11.1. In addition to showing the scores in the sample, we have highlighted the position of mu D here equal to 0. That is the value specified in the null hypothesis. Again, the null states that there would be no difference between the treatment conditions. Notice that the scores in the sample are displaced away from 0. So again, we don't see that the scores are concentrated around 0. We see that they are more concentrated around the mean, sample mean difference equal to -2. Specifically, the data are not consistent with the population mean, which was hypothesized by the null, indicating mu D is equal to 0, which is why we were able to reject the null hypothesis. In addition, note that the sample mean is located 1 standard deviation unit below 0. So let me state that again. The sample mean MD is located 1 standard deviation unit below 0. So we indicated and we had calculated the standard deviation, daisy, is equal to 2, right? And so what we're saying is, given that this is MD, from here to here is 1 standard deviation unit. And that should look familiar. This distance corresponds to the effect size measured by Cohen's d. If you recall, when we calculated Cohen's d, we calculated an actual value of -1. But technically, we report Cohen's d as a positive, so we're saying that it's 1 standard deviation unit. And again, what we're focusing on is that the majority of the scores are concentrated. And again, these are different scores, the difference between condition 2 minus condition 1. So that distribution of scores is illustrated here, and those scores are concentrated more closely around the mean difference equal to -2, opposed to the hypothesized population mean difference, which is equal to 0. So for these data, the picture of the sample distribution we see here in figure 11.4 should help you better understand the measure of effect size and the outcome of the hypothesis test. So again, we were able to reject the null hypothesis, and we computed Cohen's d as a supporting statistic to affirm that we made the correct, we drew the correct conclusion. And visually, now hopefully you can see that those d scores are more closely related to MD, which was equal to -2, opposed to mu D, the hypothesized population mean difference coming from the null hypothesis, the null. Factors that influence the hypothesis test outcome. So again, the basic structure of a t-test is the mean difference is expressed in the numerator, and standard error is expressed in the denominator. So in chapters 9 and 10, we identified several factors that can influence the outcome of a hypothesis test with the t-statistic. The same factors apply to the repeated measures t. The most obvious factor is the size of the sample mean difference, because again, that's what we're interested in. Do these conditions produce different values? And the mean difference is going to illustrate that. That's what we are interested in. A larger mean difference increases the likelihood of rejecting the null hypothesis and increases measures of effect size. So again, that would make sense that if our numerator here is very large, then our t-value would increase, and the measures of effect would also reflect that large difference. The two other factors are variability of the scores and the size of the sample, which both influence the magnitude of the estimated standard error in the denominator of the t-statistic. So now we're talking about this value. So specifically, the standard error is inversely related. Inversely means as one goes up, the other one goes down, or as one goes down, the other one goes up, just to clarify what that means. So the standard error is inversely related to the sample size. So large size leads to smaller error and is directly related to the sample variance. Large variance leads to large error. As a result, a large sample produces a larger value for the t-statistic and increases the likelihood of rejecting the null. And we've discussed this before. I have given you a little shorthand to keep in your notes. As n increases, standard error decreases and t increases. So this is representative of this statement here. So again, we've learned larger sample sizes because of the equation for standard error is going to produce lower standard error and then increase our t-value. Larger variance, on the other hand, produces a smaller value for the t-statistic and reduces the likelihood of finding a significant result. So as indicated previously, as variance increases, standard error also increases, and t value decreases. So that's represented here in this statement. And notice that there was a typo in the slide and I corrected it, so it would be a smaller t. And remember that when we're talking about the values of t, in the center is representative of the null, and so larger t's mean that they're out in the tails, which corresponds to higher likelihood of rejecting the null, and lower t values mean that they are falling closer to the center, which is representative of the null, and decreases our likelihood of rejecting the null hypothesis. So although variance and sample size both influence a hypothesis test, only variance has a large influence on measures of effect size such as Cohen's d and r squared. Specifically, large variance produces smaller measures of effect size. Smaller size, on the other hand, has no effect on the value of Cohen's d and only a small influence on r squared. And I'll repeat that one more time. Larger variance produces smaller measure of effect size. And again, we've talked about this before. When scores vary significantly, it's hard to detect treatment effects. So that should make sense. That statement should make sense in terms of variation obscures the ability to detect patterns and detect treatment effects. So large variance produces smaller measures of effect size. Small size, on the other hand, has no effect on the value of Cohen's d and only a small influence on r squared. And again, we learned that Cohen's d was developed as a way of eliminating the effects of sample size. So we recognize that when we're computing standard error, it was influenced by sample size. So Cohen's d removed that influence, and that's why when we compute Cohen's d, it's expressed in standard deviation units. So again, recognizing that variance will impact measures of effect size, and sample has no effect on Cohen's d and very minimal influence on r squared. Next, we'll consider variability as a measure of consistency for the treatment effect. In a repeated measure study, the variability of the different scores becomes a relatively concrete and easy to understand concept. In particular, the sample variability describes the consistency meaning similarities, of the treatment effect For example, if a treatment consistently adds a few points to each individual score, then the set of different scores are clustered together with relatively small variability. Again, if this ability to scream out swear words decreases the amount of pain perceived, and that effect is consistent. In other words, everyone's pain tolerance increases, thereby their report of pain decreases, let's say, by 2 points. We tend to see that consistency demonstrated in the scores that were represented by each participant. This is a situation that we observed in example 11.1 and also just reviewed in figure 11.4, in which nearly all the participants had lower ratings of pain in the swearing condition. In this situation, with small variability, it's easy to see the treatment effect, and it is likely to be significant. And in fact, we did see that it, or conclude it was significant, and we're able to reject the null. Now consider what happens when the variability is large. Suppose that the swearing in the study, for example 11.1, produced a sample size equal to 9, and the different scores consisting of these values we see here, which include -11, -10, and again, these are all different scores that were produced by taking condition 2 minus condition 1. So now the data has changed, and so now we have these new different scores. These different scores also have a mean. So the mean hasn't changed, but it was just derived by these new different scores, or D values. But now the variability is substantially increased, so that SS is equal to 288, and standard deviation is now 6. So in the previous data that we analyzed, the standard deviation was equal to 2. And now we've significantly increased the variability, and that should be evident visually. These scores are much more spread out than the previous slide we saw, or figure 11.4. Let me just go back to that. Again, see how they're more consistent. They're clustered together in comparison to what we see here. They're more spread out. So again, the mean is the same, but the standard deviation, which reflects the variability, has substantially increased. So as we did with figure 11.4, we have highlighted the position that represents the null here, which is the value specified and tested. Again, we're indicating that the population mean difference would equal 0. And we should notice that the high variability means that there is no consistent treatment effect. Again, that the large variability is illustrating that there was a different effect on these individuals. So some participants rate the pain higher, right? These scores over here on this side of the distribution. So their pain was higher while swearing, and some rate it lower, and those are the ones on the left side. In the hypothesis test, the high variability increases the size of the estimated standard error and results in a hypothesis test that produces a t equal to, so they've already done the math. We're not going to go through that. We're just going to simplify the statistics that would have been produced if this were the data that we were working with. So t is equal to 1.5, which we would not conclude as significant, and 1.5 would not fall in the critical region for alpha of 0.05 or 0.01. So with these data, we would fail to reject the null hypothesis and conclude that swearing has no effect on the perceived level of pain. So therefore, we conclude with small variability, as we saw in figure 11.4, the 2-point treatment effect is easy to see and is significantly important. And with the large variability, as we saw in this figure, the 2-point effect is not easy to see and is not significant. Again, what we've illustrated here is as variability increases, the standard error increases and our t-value decreases. So as we have noted several times in the past, large variability can obscure patterns in the data and reduce the likelihood of finding a significant treatment effect. Again, according to this figure, this visual, we see how, the effect was very different. For some, it increased their pain, and for others it decreased. So again, we can't really say that the use of swear words overall decreases the perception of pain. There's not significant data to support that. So again, in this case, because there was such high variability, we would be led to fail to reject the null hypothesis. So again, what this part of the lecture helps illustrate is that relationship. As variability increases, standard error increases, and t decreases. And as our t decreases, that means that we're talking about a t value closer to the center, and decreases our likelihood of rejecting the null hypothesis. So I tend to show these relationships, but I hope that these two figures give you a better visual interpretation of what we're talking about when we say large variability decreases our ability to reject the null hypothesis. So here's a quick summary of what we just reviewed. When treatment has consistent effect, different scores cluster together, and we see low variability. When treatment effect is inconsistent, different scores are more scattered, and we see high variability. Treatment effect may be significant when variability is low, but not significant when variability is high. Again, large variability is going to obscure the patterns in the data and reduce the likelihood of finding a significant treatment effect. Now I'd like to discuss the advantages and disadvantages of the related sample t-test versus the independent sample t-test. Notice that Chapter 9 was specific to a single sample t-test where we had population parameters, the mu in particular, but we did not have population standard deviation, but we only were testing one sample. In Chapter 10, then we realized that most research is conducted by using two samples that are representative of two different populations. And we learned that those populations, let's say for example males versus females, that the independent measures t-test was a good test to use because those two populations are distinctly different from each other. In this chapter, we learned that we're still comparing two samples that are representative of two different populations, but those samples are related in the sense that they are the same participants. So we would need to develop an understanding of when to use one t-test versus the other. Obviously, if we're comparing males to females, the related sample t-test is not appropriate because we would have two distinctly different groups that we're comparing. So we want to determine when would it be more appropriate to use a related sample t-test versus an independent sample t-test if we're not comparing distinctly different groups, as in the case of gender, male versus female. So let's begin with the advantages of utilizing repeated measures design. First, it requires fewer subjects, right? If we have one group of individuals and they're going to go through all the conditions of the independent variable, we're saving ourselves a lot of time and headache because, one, it's very difficult to recruit individuals to participate in research. So if we can use the same group of 20 individuals in all conditions in the independent variable, then it's seen as an advantage. For the independent samples t-test, if we have 20 individuals in one condition, we'd need a separate 20 in the other, meaning we'd need a total 40 participants. So again, the related sample t-test is advantaged over the independent samples t-test because of the fact that it requires less subjects. We're able to study changes over time. So again, we're using the same individual. So this type of t-test, a related samples t-test, is ideal and perfect to test before and after. So before treatment, after treatment, before they get the drug, after they get the drug. So because it's the same individuals. So that's an advantage. Whereas we wouldn't be able to do that in an independent sample t-test. We can't study people over time using the independent samples model because those are different groups of participants. Next, it reduces or eliminates influence of individual difference, and this is a very important advantage. It reduces the likelihood that when we're using independent samples, so we select two samples, they're made up of 20 individuals. So for example, sample 1, 20, sample 2 is equal to 20. And we are, let's say, testing the effects of, let's say, a tutoring program, and we're going to measure GPA after the tutoring. Well, let's say just by chance that these individuals, we randomly selected them, but just by chance they tended to be the smarter students, the more studious students, the students that try harder. And just by chance, this group of individuals don't share those same characteristics. So in the end, we may be misled to believe that the treatment was effective, but when in fact we had a different makeup in the samples. And again, that just may occur by chance. And when we're working with the same individuals, you can see that is eliminated because the characteristics that those individuals bring to the table, they will bring with them to each condition of the independent variable. So in a sense, we're holding those characteristics constant. So again, I'll repeat that the same individuals will bring the same characteristics to every condition of the independent variable. And so we don't need to worry about this possibility that one group is better, they're faster, they're smarter, they're more motivated, whatever it may be. We don't need to worry about that because it's the same people. And as a result, consequently of that, we have less variability in the scores. And that should make sense. Again, I just said we're holding those characteristics constant. So the variation between the samples is going to be decreased. And as we've been saying for quite some time now, low variability is the ideal. We want low variability because high variability obscures the effects of the treatment. So if we can hold certain characteristics constant, then that's going to reduce variation, which is a good thing, which is why this is seen as an advantage. So technically speaking, the related samples t-test is better. If you can utilize it, it is better because of this point in particular. It will reduce the variability, but recognizing that sometimes it's not possible. If I'm looking at the differences between IQs of engineering majors and psychology majors, those are completely different populations, and therefore I'm unable to utilize a related sample t-test. So now let's discuss some of the disadvantages of the repeated measures design. So factors besides treatment, so other variables, right, may cause subjects' score to change during the time between exposure to the treatments or between measurements. So again, let's say we're testing out a new treatment for migraines, and we expose them to one type of treatment, one group of, let's say, 20 individuals, and then they do that for, let's say, 6 weeks. Let's say they're using an increase of magnesium in their diet, and they do that for 6 weeks. And then they take a little break, and then we try something new that's been advertised a lot, let's say Botox for the migraines. Well, in between that time that they are exposed to condition 1 and then condition 2, some things may change, and their migraine frequency and severity may be influenced by other factors, and that is due to the time lapse that has occurred. So when we're using independent measures t-test, those two conditions are being exposed simultaneously at the same time. So one group receives the magnesium, the other one receives Botox, and we measure them at the same time. But if we're using related sample t-tests, we have to use one treatment for an amount of time, and then we start them and expose them to the other treatment. So the lapse of time can muddle the results, could have an impact on the scores. In this case, if we're measuring the number and severity of migraines that these individuals are experiencing. So that's a bit of a downside because those conditions are not occurring simultaneously. The results may not be as clear as we would like. Next, participation in the first treatment may influence the scores in the second treatment. We refer to that as order effects. So something like a learned behavior. There's another video under the examples that I go through that illustrates, let's say we're trying to improve someone's golf game, and one coach believes that visualization techniques really help you get that ball in the hole. And another coach thinks that relaxation techniques are more effective. And so we have a group again of 20 individuals, and they learn this visualization technique for, let's say, 6 weeks. And we measure the effect on their golf game. And then we have them learn this new relaxation technique that this other coach thinks is superior. And then we measure their golf game at the end. Well, by the time they get to the second condition, when they golf, they may be utilizing some of the other things that they learned in the first condition. So when they're golfing, they may not, you can't erase someone's brain or what they've learned. And so they may be subconsciously or consciously using the visualization techniques that they learned in the first condition and applying them with what they're learning in terms of the relaxation techniques. And so in the end, we may see that condition 2, in this case, the relaxation techniques, may produce superior golf scores, but we cannot tease out whether it was strictly due to the relaxation techniques or if those participants combine the two techniques. So you have to be conscientious that if individuals are learning something, the related sample t-test may not be the optimal test to apply because of this fact that we can't erase what they've already learned. And whether they want to or not, they're going to tap into that in the second condition, which may inflate the scores, in this case, the golf scores, or improve their golf scores. In golf, you want lower scores, but regardless, you would have an influence on the scores in the second condition. So you have to be conscientious of that. As a way to kind of address this, the order effects, that is, we can engage in counterbalancing. So counterbalancing is a way to control time-related or order effects. And so what we would do is expose, let's say we have treatment 1, treatment 2, so we have 20 of the individual, let's say we have a total of 20, and we have 10 individuals first go here, and the other 10 start here. And then they switch. So then they go to this condition and they go to that condition. So we're counterbalancing the order effects. And so that in some regards may help minimize the negative influences of using the related sample t-test because of the fact that they're taking information with them. But if we take the 20 individuals, split them in half, and expose them in the reverse conditions, then that's a way of kind of holding those influences constant. So they are taking, these individuals are taking what they learned here and taking it with them over here. These individuals are taking what they learned here and taking it over here with them. So again, that's this idea of counterbalancing what they've been exposed to. And hopefully those things kind of cancel each other out, and we can still see the effects of one condition versus the other. And that's nice to do when you're working with the same individuals, because again, all the other characteristics that they bring to the table are being held constant, again, reducing variability. Now, another way of combating the order effects is to use what we talked about earlier in the chapter, which is the match subject design, where you're taking that person's twin, not their exact twin, but someone that looks very similar to them, and exposing them to these different treatment conditions. So again, the match subject design is a hybrid. You've got two different groups of samples, but they are almost identical to each other. So then you would utilize the techniques for the related sample t-test. So that's a good solution to this possibility of order effects. But if there's any reason to believe that the order effects are going to be very strong, or there's some lapse of time effect that you cannot combat, then it's always better to go with the independent measures t-test opposed to the opposed to the related sample t-test. Again, between the two, the related sample t-test is better because of the fact that it reduces variability. But again, we recognize this in some cases, this is our only option, and that's okay. It's just we are discussing the advantages and disadvantages of both. And finally, we'll review the assumptions that pertain to the related sample t-test. So as we've discussed in previous t-tests, observations within each treatment condition must be independent, and then the population distribution of d-scores, or difference scores, must be normally distributed. And technically speaking, this assumption is not typically a serious concern unless sample size is very small. With a relatively large sample, anything greater than 30, this assumption can be ignored. So again, we do require that the distribution d values must be normal, but as long as we have sample sizes larger than 30, then it's not anything that we need to worry about. So we'll end with a learning check. Assuming that the sample mean difference remains the same, which of the following sets of data is most likely to produce a significant t? It's a perfect learning check given what we've presented in this last lecture for Chapter 11. So ideally, we want large sample sizes. So of these, we would omit these two because these are larger. And so we want large sample sizes because that produces a smaller standard error and a larger t value. And then the other variable, again, we're saying that this is going to be constant. So the other variable is variability, and sum of squared deviations is an illustration of variation or variability. So I'll ask, do we want high variability or low variability? And I hope you said low variability, because I've been hammering that in for quite some time now. So low variation would be ideal. So again, we would, in comparing these two, right, we would not opt for that one. We would prefer this scenario because we have larger sample and we have lower variability, which is going to help us detect treatment effects much better than if we had higher variability. Next, true or false? Compared to independent measures design, repeated measure studies reduce the variance by removing individual differences. And we just went over this, so I hope that you answered true. That's one of the advantages of the repeated measures, is that it reduces the differences between individuals. All of those characteristics are held constant. So again, it's one of the advantages of the repeated measures t-test design. Next, the repeated measures t-statistic can be used with either the repeated measures or matched subject design. And that is true. The equation that we use to compute our t for the repeated measures, which is md minus mu d over estimated standard error of the mean difference, that if we're using the matched subject design, that this is the way we would calculate our t, even though we recognize that we have two different groups of individuals. They've been matched one for one, so we would treat them as if it's a pair or one individual in two different conditions. So again, for the repeated measures t-test and matched subject design, we would produce our t statistic using this equation. So this is a true statement as well. And that concludes the lecture for Chapter 11. If you have any questions or concerns, as always, please email them to me or post them to the discussion board in which you find these videos.